Hello everybody. In this video presentation I will show you how to apply a surrogate modeling toolbox, also called SUMO, to efficiently optimize a wireless network problem. The content of this video presentation is summarized as follows. We will start by giving examples on the wireless network optimization and the design parameters and objectives used to tune the performance. Next, we will show the two broad optimization approaches called exhaustive searching and efficient global optimization. And then we'll show their pros and cons. After that, the principles of the SUMO toolbox, which is again from this efficient global optimization domain, will be discussed. We will also look at the inside of the SUMO toolbox, and then we'll discuss the integration work we made to a wireless testbed. Finished with the principles, we will explain a wireless conferencing scenario that's going to be optimized. And to this end, two experiments will be shown, one with the exhaustive search approach and another with the SUMO toolbox. And during the SUMO optimization, we will compare its performance with the exhaustive approach. And finally, we'll show you how the SUMO toolbox can be used in a wireless testbed. Okay, let's start. As an end user, we have specific objectives from the wireless solution we use every day. For example, we might want to have a good audio quality in a wireless conferencing system. Or we might want to spend less energy and at the same time maximize coverage of wireless sensor networks. So, such and other applications require tuning of a number of parameters to get the optimum settings. If we look at the wireless conferencing system, for example, possible design parameters could be transmission power, transmission channel, data bitrate, modulation type, and others. Moreover, wireless solutions usually consider multiple contradicting objectives. Transmission exposure, for example, can be used as a second objective in this wireless conferencing system. Transmission exposure measures the level of electromagnetic radiation from a source as seen by a receiver. Generally, exposure favors with decreased transmission power. It will counteract the quality of the audio. Therefore, with a number of design parameters and contradicting performance objectives, we optimize wireless solutions to achieve the best settings. Usually, traditional methods called exhaustive searching methods are applied. Exhaustive searching methods consider every possible combination of the design space and they compute the performance. At last, we will select the design parameter that give the optimum performance. Okay, such methods are effective in a sense. They locate the optimum settings with 100% accuracy, but the downside is it takes a very long time, especially when the number and range of the design parameters increase, then optimization will become impossible. The second alternative is to use efficient optimization algorithms. These algorithms work by efficiently selecting as few points as possible from the design space and they arrive at the optimum settings in a very short time. There are a number of such algorithms widely applied these days. For example, genetic and differential evolution algorithms, particle swarm optimization, simulated annealing, and surrogate modeling or SUMO, which we'll see next. SUMO toolbox internally applies the famous expected improvement, in short called EI, to arrive at the optimum settings. The algorithm It will start from initial sample points of the design space, and it generates the first surrogate model. For example, if we consider a two-dimensional design space problem, the SUMO toolbox will generate an interpolated surface from the selected sample points. After that, the SUMO toolbox predicts the next sample point from the surrogate model, expecting it will improve the system performance. This process is iterative, and each time increasing the sample points, the surrogate model better approximates the system, and also speeding up the search for the optimum settings. So, SUMO, out of the box, it has two major parts, the surrogate modeling part and the controller managing the optimization process. The SUMO toolbox is designed to work as a standalone optimization module, and there are a number of practical examples applied with it. For further information, you can follow the link shown on the screen. However, in the scope of crew benchmarking tools, we want to use SUMO inside our experiment execution tool. Later in this video, I'm going to show you what this experiment execution tool is and how we will apply SUMO with it. In a nutshell, the overall aim of this execution tool is to conduct wireless experiments using a number of optimizers. The different optimizers are first modified from their original form such that they have clear interfacing inputs and outputs. Then the execution tool orchestrates the optimization process. So for the SUMO toolbox, we've removed the controller part, created a clear inputs and outputs, and finally plugged it into the execution tool. Currently, this toolbox is it's used in the iMinds testbed, which is located in Ghent, Belgium, and we'll show you how we will use this for optimizing a wireless network problem. Okay, now let's look on a wireless conferencing system. A wireless conferencing system is composed of wireless microphones, where a speaker broadcasts his voice over the air to a number of participants, and at the other side, each participant receives the broadcasted voice through their wireless speaker. These days, we see such scenarios in multilingual conferencing systems, such that the broadcasted audio contains multiple translated audio streams from the speaker, and each listener selectively tunes to their preferred audio stream. However, such a conferencing system has a number of challenges, and let's see two of them here. The first one is the audio quality perceived by the listeners. These days you see access points mounted everywhere in a conference room, train stations, internet cafes, which all of them creates interference on the surroundings. So the first thing we want to do is limit such kinds of interference on our wireless conferencing system, which at the same time, if we do that, it will increase the quality of the audio. Second, transmission exposure has to be reduced on each participant. This is a recent concern getting more and more attention, and even on some places, you'll see there are limits to reduce the human exposure. So we choose these two objectives because they contradict to each other, and combining them creates a trade-off where we want to locate the optimum. Finally, we will tune the speaker's transmission power and transmission channel in search of increased audio quality and minimized transmission exposure. The straightforward approach will be to do experiments at each parameter setting and see which one will give the highest combined objective. So to this end, there are 13 channels in the Wi-Fi ISM band, actually in the 2.4 gigahertz ISM band, and a normal Wi-Fi antenna can transmit at 20 different power levels. So the maximum possible parameter combination will be 13 multiplied by 20, which will give you 260 parameters. And the output you will get if you conduct all these things will look the following. The two figures on the left, which are piled on top of each other, are the individual objectives. So the one on the top is the audio quality, and the one on the bottom is the transmission exposure. And the right figure is the combination of the two, indicating the combined objective. The color bar indicates the respective objectives in a scale of 0 to 1, or as you can see, it's from blue to red. So if you see red, it means you have the best performance, and if you see blue, it tells you that you are in the worst performance. You can see the right figure that the system performance is located somewhere between channel 7 and 8 and transmission power 1 up to 3. Indeed, this area has a better audio quality setting with a very limited exposure. However, as we have discussed earlier, such methods take a long time, a huge amount of time, especially when the design parameter increases. So now let's start the SUMO optimization experiment using the same scenario and see how long it will take before locating the optimum settings. On the screen, we see three areas that I used to explain the SUMO process. The left top screen shows the radio environment map called REM of the experiment. It will use RSSI, or Received Signal Strength Indicators, which is derived from the wireless nodes, and then it will draw the radio environment map. On the right hand side, you see a command line interface of the experiment execution, and behind the scene there is an experiment controller executing the experiment, and each time outputs are forwarded to the screen. The experiment description is a file which holds the orchestration details, which is used by the experiment controller. The format of the experiment description is dependent on the experiment controller used, and in our case we use the OMF controller to orchestrate an OEDL script. OMF, it's a testbed management and controlling framework, and it's developed by the NICTA Research Center in Australia. On the bottom screen, you see two graphs to indicate the progress of the SUMO experiment. The bottom left figure is the SUMO objective model, and it's comparable to the exhaustive search model we saw in the previous slide. The bottom right figure draws two curves on top of each other. The blue curve shows the performance of the SUMO experiment in a normalized scale as compared to the exhaustive model. And here a value of 1 on the curve means the SUMO experiment arrives at the optimum settings. But you have to bear in mind that this is not the case for a general problem, since we don't know the exhaustive model beforehand. On the other hand, the green curve shows a standard deviation performance, which is calculated for assorted and largest values. This metric can be used as a stopping criteria because it uses a relative performance, a performance difference between SUMO experiments, and it does not depend on the knowledge of the exhaustive model. At the optimization approach, the optimum region, the sorted top and values will have comparable performance among each other. So if they have similar values, which means their standard deviation will be very low at the same time. You can refer the literature shown on the screen for further details. As you might have guessed, we have fast-forwarded the video so that you can see the complete optimization process. By letting a lower bound at 0.032 and taking the last 5 elements, the SUMO experiment stopped at the 28th iteration, and we get 95% performance accuracy. Hence, we achieved around 9.2 faster performance compared to the exhaustive search model. Now let's see how you can use this tool for your experiment inside the testbed. But before you begin, you need to have a VPN account on the YLabT testbed to use the SUMO toolbox, because everything what follows after requires a VPN account. And in order to do that, you have to send email to the admins of the YLabT testbed, and once they give you access, you can continue what comes after this. Alright, we've mentioned earlier that the original SUMO toolbox has been modified so that it fits with the controlling framework. And due to this fact, there are two options that optimizing experiments can make use of it. The first one is to use it within a controller, or to put it in a controller of your choice. So for this option, everything is included inside a MATLAB script, and this script reads a file which contains experiment datasets and starts the surrogate modeling. After the modeling is finished, the tool applies the EI criterion, the one we have discussed earlier, and it will provide us with the next sample point. This is one iteration of the optimizer. And next we conduct experiments using the next sample point, and we will store the result back to the file for the next optimization to continue. With this approach, you have the choice to use your own controller, select a variety of initial sampling methods, or you can define your own stopping criteria. In sum, the interface to this SUMO toolbox is very simple. Add samples and values to the file and call the wrapper MATLAB program. Wait until the optimizer finishes, and then retrieve the new sample again from the same file. And then you can continue until the stopping conditions are fulfilled. The other option you have is to use the crew execution tool. And the modified SUMO toolbox is one of the many optimizers integrated. The execution tool interface is web-based, and optimizer configuration is started once an experiment description file is passed. This file contains a list of design parameters that are going to be tuned, and objective variables where we're going to create the combined objective out of. The execution tool will then start the experiment using the first design parameter, and after that it calculates the combined objective. Next, it will call the SUMO optimizer, which it internally calls the previous MATLAB script we have seen, to calculate the next sample point. And using the next sample point, the execution tool again conducts a second experiment, and this process continues until the stopping criterion is satisfied. There are two stopping criteria defined for the SUMO toolbox. These are the standard deviation and the fixed iteration stopping criteria. And for each stopping criteria, you have to write appropriate values on the text box next to it. The other configuration provided for the SUMO toolbox is the initial sampling. This configuration gives the option to select the number of initial samples, before conducting the optimization, and how the initial samples be selected from the design space. To this end, the famous Latin hypercube sampling is provided, and also a custom sample selection is also provided. And finally, the SUMO toolbox runs on a MATLAB server, so you need to have, or you need to provide the right credential to this server. As a final note, this experiment execution tool is part of the crew benchmarking suite, and I really encourage you to follow the tutorials which is found on the link shown below. Thank you for listening.